So here it is told that let A be the set which contains the elements 1, 2, 3, and then we have to find the number of equivalence relations containing the ordered pair 1, 2. So now the set A cross A is the universal relation on the set A, which will contain 9 elements, which are 1, 1, 2, then 1, 3, and then 2, 1, 2, 2, then 2, 3, and then 3, 1, 3, 2, and 3, 3. So it will contain 9 elements. So now we know that for R to be an equivalence relation, it should be reflexive, symmetric, and transitive. It should be reflexive, symmetric, and transitive. So this is the rule. So for transitive, the rule is what? For R to be transitive relation, we should have that if A1, A2 belongs to R and A2, A3 also belongs to the relation R, then that implies that A1, A2 should also belong to the relation R for all A1, A2, A3 belongs to the set A. So R to be a transitive relation on the set A, then this condition should be fulfilled. Then for R to be a symmetric relation, on the set A, if A1, A2 belongs to the relation R, then this also implies that A2, A1 should also belong to the relation R for all A1, A2 belongs to the set A. So then we can say that R is a symmetric relation on the set A. And then for R to be a reflexive relation, on the set A, we should have that all A, comma A should belong to the relation R for all A belongs to A. So now it means that here in this case, the set A contains the elements 1, 1, 2, 2, and 3, 3. So this should be present for R to be reflexive. And then for symmetric, 1, 2 should be there and 2, 1 should be there. Since why here it is told that 1, 2 should be there. So 2, 1 should be there. And it is not told that 1, 3 should be there. So we can skip it. So 1, 3 is not there, then 3, 1 should not be there. These two should not be there. And if 2, 3 is not there, then 3, 2 also should not be there. But here it is told that R should be an equivalence relation, so it should be transitive also. So it means that if 1, 2 is there, and so 2, 1 is there, so 1, 2 is there, 2, 3 is not there. So we don't have to think. So therefore, one relation we can get like this. We can get one relation R1. So that can be like 1, 1, 2, 2 should be there, 3, 3 should be there for R to be reflexive, R1 to be reflexive. And then it should contain 1, 2 it is told. So 2, 1 also should be there. So it is reflexive. So then it is reflexive also. It is symmetric also. Since 1, 2 is there, so 2, 1 is also there. And 3, 1 is not there, so 1, 3 is also not there. These 4 are not there. So it is transitive also. Since why 1, 2 is there, since why 3 different elements is not there actually, since means 1, 2 is there and 2, 3 is not there. So it is transitive also. So this will be an equivalence relation. And then one more example we can have, like suppose the relation R2, I can say like I can have 1, 1, 2, 1, 1, 2, 2, 3, 3, and I should have 1, 2, and so 2, 1 also I should have. And then if I have 1, 3, then 3, 1 also I should have. So 1, 3 is there. So 2, 1 is also there. So 2, 3 also should be there, since why it should be transitive also. So therefore I can't end here. So 2, 3 also should be there. And here also 3, since 2, 3 is there, and it should be symmetric also. So 3, 2 also should be there. So it means that the entire set A cross A is coming. So the entire set A cross A also I can take, which is the universal relation. So the universal relation itself, it is a equivalence relation. It is also an equivalence relation. Or we can take this relation R1, which is a subset of A cross A. So that also I can take. So only two such equivalence relation can be formed on the set A, which contains 1, 2, which should contain 1, 2. So therefore, B is the correct answer. So hope you have understood. Thank you.